For this problem, looking at a shaft which is carrying two kinds of loads. One is an axial force P, the other is an axial torque T. What we want to do here is to determine the principal components of stress and the maximum in-plane shear stress. So what we will do, we will follow sort of our three-step plan here on first looking at the internal load. We will make a cut through the shaft, let's say somewhere along there. The resultants that we're going to have, it will be exactly what's acting there on the end, a load P and a torque T. Second thing, when we look at our stress distribution, the load P, that's simply going to give us a constant stress, normal stress on the face. I'll draw this out as sigma, where sigma is simply equal to P over A. And since A is equal to pi r squared, that's d over 2 squared, that's going to give us 4p divided by pi d squared. The other component is going to be that due to shear. Any point that I pick, this one or this one or that one or that one, the magnitude, the shear stress will be the same. The magnitude is going to be tau is equal to the torque times the radial distance out to those points, d over 2, divided by IP, where IP is equal to pi over 2, r to the fourth, so that's d over 2 to the fourth. So our shear stress at any point on the circumference of that is going to be the same, 16 t over pi d cubed. The difference is going to lie in the direction. If it's that point, it's there. If it's a point there on the side, it's up. If it's the point on the top, it's to the left. Point on the right is down. So any point that I choose is going to be the same. So I'm in the process then of, I guess, drawing my stress cube. What I'm going to do is choose, let's say, an element somewhere here. In fact, let me be more precise there. Let me choose this element right there. So that element will have a normal stress of sigma, and that will have a shear stress down, because that's really this point right there. As I fill out the other three parts, this is what I get. With this, we're in a position, therefore, to work with our stress transformations. We know that sigma average is one of the two things we need, so that's just sigma over 2, so that's 2 pi over pi d squared. R is equal to sigma over 2 squared plus tau squared. So that's the square root of 2p pi d squared, that quantity squared, plus tau, which is 16t divided by pi d cubed, all that quantity squared. When I square and combine and factor out some terms, I'm going to end up with a 2p over pi d squared, the square root of 1 plus 8t over pd quantity squared. Now this is an important way to write this result, because it's quite clear from here, since we've got 1 plus a positive number on the inside taking a square root. This number here is always going to be larger than 1. What this means is that when we compute our two components of principal stress, this is going to be sigma average plus R, and that's going to end up being 2p pi d squared, 1 plus the square root of 1 plus the positive number of 8t over pd squared. And the other principal component of stress, sigma P2, we know is sigma average minus R. In this case, being we know about the size of R, we know that the sigma P1 is positive. And since this number here is greater than 1, this number is negative. So when we draw our Morse circle, we know it's going to extend over there on the left-hand side. We also know that tau max absolute is going to be tau max in plane, and that's equal to R. And the reason we know that is because our sigma P1 and sigma P2 are of opposite sign. Therefore, or maybe not therefore, but to show this, I will draw the Morse circle the best that I can, and that's going to be a circle, a radius R, which we've found. Of course, the center is there at sigma average. The first principal stress is sigma P1, and then the sigma P2 again is a minus because of the arguments that we gave above. So here the combined state of stress was not too complicated. The properties of that are the same for any point on the circumference of that rod. We simply wrote down the axial component, P over A, added on the shear stress due to the torque, which is the torque times the radius divided by IP. And we used our results from before for calculating the principal components of stress from sigma average and R, and also our tau max absolute in this case ended up being R.